Hi everyone, and welcome to our third webinar. Um, if you are following us, then it's nice. If you're new to this, I hope you'll enjoy our discussion, our presentation, and all. So today, yeah, before that, wherever you are, good morning, good afternoon, and hope you are doing well because I am right now in Toronto and it has a massive winter storm coming right now and is also happening. So anyway, I think everyone's safe right now. So today's discussion is a little bit, what do we say? It's not really geology based. So we wanted to touch more about the model building applications, how you can build model, what are some components that you should always be looking for while you are training a model, and things like that. So we three have been doing a lot of this machine learning model building applications for a while now. So I will go through some high level presentation today. What It's mostly like sharing our experiences, which has worked for us, which hasn't worked for us, or why one optimizer is better than the other, and why you need a learning rate, a particular learning rate, or maybe like which learning rate is better for what kind of applications. These are based on mostly our experiences, and then we'll go through a Streamlit application. So, and which will show you how if you have a very simple objective functions and how if you implement these optimizers, it's going to work, and how well are these optimizers behaving, how well are they converging to a minima and things like that. So hope you enjoyed the like you also have a hands-on experience on this visualization code that we developed, like the application. And one way is like also to we did develop this because it's quite nice and easy to build it in Streamlit. So we'll also share this while the presentation is going on. So maybe I'll just hand it over to Kwame, our senior AI engineer, and who will drive today's conversation. And I will then go into showing the notebooks and applications uh, and things like that. And later on, we'll just go with a round of discussion. Your experiences would also be appreciated. Okay, Kwame, you can take
Yeah.
over.
Hi everyone. Hi everyone. So today's presentation is maximizing models performance, a deep dive into optimizers and learning data schedules. So we will be looking mildly into these two concepts of machine learning. Why do we use optimizers, and where exactly do we require to use this learning rate schedulers? And these two are mostly used to maximize the model's performance to further fine-tune it. So as mentioned earlier, the agenda of this presentation is first we will discuss what optimizers are and their types, and then what the learning rate schedulers is and what are the types. And then moving forward, we will, as already mentioned by Tanisha, we will have an overview of the notebook as well as the Streamlit app which you can play with. And finally, we will conclude this presentation. So what are optimizers? So basically optimizers are just a mechanism through which we adjust the weights of our neural network, weights and biases of neural network so that we can get the minimum loss so as to increase the performance of the model. And there are many optimizers that are available, and each one is having some strengths and some weaknesses, and we have to decide on which optimizers do we need to use based on some initial model training, seeing how the model performance is, and based on that, we have to make the decision. So in this particular presentation, we will be looking into four optimizers. One is gradient descent, another one is Adam, then RMS plot, and then Adam max. So here is the first optimizers that we will be discussing with. So in any machine learning algorithm, this is a very popular optimization algorithm, and this is considered as a starting point of any machine learning model, where we just simply plug in this SGD, stochastic gradient descent optimizers, and then we see or assess how the model's performance is. And this is basically a first order optimization, which basically takes first order derivative of the target objective function and then uses this to back propagate the loss. And basically, we iteratively update the weights of the linear effort using this optimizer or any other optimizer. And there is one disadvantage of this optimizer, and that is basically that it can get stuck in the local minima. And if you do not carefully tune your model and if you do not carefully use the correct learning rate, then you might get stuck in the local minima. So you have to be careful for that. And due to these lack or disadvantages of this gradient descent algorithm, we will be discussing few other optimizers. And you can look into the algorithm as well. This I have taken this screenshot from the PyTorch uh, documentation. So the second one is RMS prop, and what it does is it learns. So earlier in this gradient descent, we are using a learning rate, and then we are using that learning rate to optimize all the weights. But in RMS prop, what we do is we learn the learning rate of each parameters separately. So and we adapt the learning rate for each weight based on the average of recent magnitudes of the gradients. So based on the gradients, whatever we are calculating with respect to loss, so we adapt the learning rate for each weights. And the ability or the advantage of RMS prop is to handle non-stationary objectives and its quick convergence rate. SGD, on the other hand, is sometimes slow to converge, and due to this reason, we use RMS prop and ADAM or ADAMAX, which we will be discussing further. And again, as already, I mean, similar to the disadvantage of SGD or gradient descent, we also have a similar problem with RMS prop. Is basically it can get stuck in local minima, so you have to be careful while doing hyperparameter tuning. Moving on to the third optimizer, it's a hybrid optimizer actually, ADAM optimizer, and based on ADAGRAD and RMS prop, where again it computes the adaptive learning rate for each parameter instead of relying on a single learning rate itself. So it calculates the adaptive learning rate for different parameters, and the advantage over here, as similar to RMS prop, is it can converge fast and it can also adapt to sparse gradient. One disadvantage is it can shoot the minimum or basically the global minima. If you are using a high learning rate, then it is very much possible that you might shoot out from the global minima. So again, you have to be careful with all the different small parameters that you are using in your model. And finally, this is the last optimizer that we will be discussing. So it is similar to Adam optimizer, but instead of using L2 norm in Adam optimizer, here we use infinity norm. So hence the name AdamX. So basically, again, what it does is it computes the running average of the infinity norm of gradient, and again, it adapts the learning rate for each parameters separately. And similar to Adam Optimizer, it also has a similar problem of overshooting the minimum. And you can again, you should look into all these algorithms so that you can better understand how the working of each algorithm is. Okay. So here we have our first trivia question. So which of the following statement is true about stochastic gradient descent? Stochastic SGD updates the weight after each batch of data is processed. B is SGD always converges. SGD is not suitable for large data set, or all of both. So maybe comment your response. What do you think is true about SGD? Does it updates the weight after each batch, or can it reach global minimum?
Five seconds, and
Do
then
give
we'll
your response
if
in
then there
comments.
is the answer. I'm hoping. I guess it's Friday. People are a bit anxious,
Yeah.
so let's show them the answer.
Okay. I think there is some error in the presentation, but the correct answer is SGD
All of the
updates the
above.
weight for each batch of data is processed. No, not exactly. It's SGD updates the weight after
So,
each
wait.
batch of data is processed.
Mohit Kumar gave the
Yeah,
right answer. Very good. Well
essentially.
done, Mohit.
Mm.
Awesome. Wonderful. That's the spirit.
Okay. Okay. So coming to the next section of our presentation, learning rate scheduler. So if you don't use the correct learning rate, or if you continue to use a constant learning rate, what can happen is either you might wander from the global minimum or overshoot it. So you have to adjust your learning rate according to the model's performance at that particular iteration so that you can achieve the global minimum. So this is what learning rate scheduler does. It adjusts the learning rate during the training in order to improve the model's performance. And as already mentioned, this learning rate is what determines how much weight and license are going to be updated during the batch update. And there are several learning rate schedules out there. And again, as already mentioned, it is used to fix learning because a fixed learning rate can result in slow convergence or oscillation or divergent behavior, as already I mentioned. And it can, using this, it can improve the convergence rate, prevent overfitting, and help find model global minima. Okay. So there are few important learning rate schedulers, and all the usage of all these types of learning rate schedule depends upon the need or how your model is performing and what all things do you want to do. So it depends upon different scenarios. So you have to choose it accordingly. So these different types of learning rate schedulers are like step scheduler, exponential, or cosine annealing, or reduced learning rate on plateau. So this particular image that you see, this is for a step scheduler, and it reduces the learning rate by a fixed factor. So let's say that you have set a fixed number of epochs at 10. So what it's going to do is, like after each 10 epochs, it's going to decrease the learning rate with a fixed factor with whatever you have defined. And exponential scheduler, what it does is it again decreases the learning rate, but in an exponential fashion instead of the fixed factor that is used in a step scheduler. And in cosine annealing, what it does is it reduces the learning rate according to the cosine function instead of simply using the step learning rate or exponential rate. And reduce learning rate plateau reduces the learning rate if your validation, let's say if your validation has stopped increasing, has stopped decreasing, validation loss, then you wouldn't want to overshoot from that global minima. So in order to be at the global minima, you have to decrease the learning rate over there. So this is where this particular learning rate comes into play, that you reduce the learning rate when you see a plateau in the validation loss curve. And as I already mentioned, each type of learning rate scheduler has its own use case and based on the specific requirement of the training process. So this is the
So,
second
Kwame,
area.
maybe we can just probably discuss which one do we are we using mostly on the
Yeah,
learning rate. Yeah, one
yeah.
learning rate
So
scheduler
basically,
is. Mm-hmm.
so most of the time you would want to use reduced learning rate on plateau because if your validation loss has already stopped improving, then you wouldn't want to continuously, I mean, based on the initial learning rate, you want to increase you want to update the weights. So the very first thing that you can try is reduce learning rate on plateau. You can also, if you're using Adam Optimizer, so Adam, as already mentioned, that Adam Optimizer always tries to find, I mean, it can quickly or fast, there is a fast
Mm-hmm.
convergence rate in Adam Optimizer. So you can fix a, let's say you can do a number of epochs at 10. So basically you can decrease the learning rate to 1/10 after each 10th epoch because it converges faster. So that way you can, update the weights accordingly instead of overshooting the global minima. So yeah.
Mm-hmm. These we were using for the more of the computer vision studies, right? Actually,
Yes.
yeah.
Yeah.
Okay.
So
So let's go
second
to question two.
trivia
Yeah.
question. Yeah. So which optimizer is a variant of stochastic gradient descent? Optimizer that uses a moving average of gradient instead of the gradient itself. Which optimizer is a variant of SGD optimizer that uses a moving average of gradient instead of gradient itself? The options are ADAM, SGD, ADAGRAD, and RMS Pro. Okay, so the correct answer is RMS Prop because as I already mentioned, it is similar to SGD, but it updates the weights of each updates the learning rate of each weight based on the moving average of the gradient. So I think Tanisha will talk about basically give you a hands-on demo and then finally show you the Streamlit app that we have developed.
Okay, just maybe before I jump in, I know it's good to sort of, I understand that some of you are just beginning with your journey. And Kamoga, for example, your question is fair because as more and more people are entering machine learning and deep learning field, it is becoming increasingly sort of exciting to kind of and overwhelming. So both those things you have to pay into account. It is exciting because the field you hear about it all the time, but it's overwhelming or daunting because you don't know where to start. So, for example, Kamoga, I think it's a very good question you ask. Typically, there are many simple, not simple, there are websites or platforms like Coursera. Andrew Ng has a very good course of neural networks. It's probably one of the most popular courses out there. I've personally enjoyed listening to Andrew in the way he explains about it. So, big data obviously becomes more practical when you start creating data sets and then you start actually using these techniques, which we are talking about right now. And there is also, we have our own course. It's a self-paced course. I can, after this Streamlit application, which obviously will give you a bit of more perspective about the optimizers, about how to sort of use early stopping and all these interesting techniques to kind of start, saving your models and model files at the most optimum state, which is, of course, the goal of any machine learning project. I will share with you in the end a little bit of the link of our Applied AI Essentials, and there you can take a look at it as well. We have designed this Applied AI Essentials because we think that learning fundamentals like you're learning now a little bit is good, but it's not really getting the job done. We also believe that jumping into your industry domain and trying to solve the problem without having a good understanding of what is, if you're in an oil and gas business or manufacturing or supply chain or some other field, then it becomes only more complicated because you see big data in many forms. So what we designed our training program was applied AI. So, how to apply AI and then create an essential pack out of it, meaning the only things that matter you should learn. And then learning these techniques, which we are talking about, like optimizers, learning rate, and all the other hyper parameters. That's what they're called. They are not network parameters. So the hyperparameters like learning rate, optimizers, and there are a bunch of other functions like regularization, etc. Then things become very exciting because then you actually start knowing what to tweak, how to tweak. This webinar obviously may not answer the question right now, but I would suggest one, go to Coursera and search for neural networks program. That's a Stanford program, and I will share the link later here, and then perhaps maybe I can share it already in the chat, and you guys can take a look at it while my colleagues proceed with the demo. So I will copy and paste it here, but it's a very good question to ask. So I've just copy pasted it there, and you will be able to see it here. This is the link. It's a self-paced program.
Maybe Terry, after this demo, we can just go to the website.
We can go to the website.
Yeah, so, we'll just do that. Yeah.
So perfect. Go ahead. I just want to make sure that that's been addressed.
Sure. So I will take over from 𝗁𝗲𝗃 and we'll go to our GitHub. So all the presentations and the notebooks that we have been sharing is in the GitHub. So let me start sharing. Okay. Okay. So so this is our third webinar, but if you already go to this GitHub link over here, the 𝗟𝗲𝗃 webinar, that's the name of the repo. So you can actually see all the presentations that if you click on this icon, it redirects you to those presentations. And this is also linked to the PowerPoint and all. This notebooks are already being uploaded here. It's in the notebook folder over here. Then for today's talk, this is our third webinar. So we still haven't uploaded because we'll kind of upload it after the talk, but it's the optimizer app already over here. And we're just giving you a sneak peek for what you can expect for the next few webinars. So we will go to the notebook, and here we created a very simple application. So our objective function is x² plus y². And how do you minimize that? So this is basically the objective function that we plotted in 3D. And then we are using all these 4 different optimizer techniques that 𝗁𝗲𝗃 described. It's a little complicated when you apply for loss functions and all. So here, so that's the reason we took a very simple objective function and try to show how it's working. So probably good idea. You can also go over here. It opens in, you can open it in Google Colab and run it by yourself. There's no dependent utility function, so it should run by itself. It shouldn't be a problem. Not running it right now, but if you, of course, have any problem, you can reach out to us. So, okay, let's just go quickly over this. It's a very nice notebook that 𝗁𝗲𝗃 made with more like what are objective functions, what are the derivatives. Like derivative is quite easy for x² plus y², but it talks about this the step size, momentum, and all. So these are all set to the number of iterations is 60 for all the optimizers. And right now we have used default values, like these are values that have proven to converge, but of course that's not written in stores. So you can definitely like adjust it accordingly. So we did run the notebook, and then it's showing how it traced the path to the minima. And over here it's similar. So because it's quite, yeah, so it goes into different minima positions here. So maybe I'll just go into that Streamlit application that one of our intern developed. So let me stop sharing this and we can share the URL to the application. I hope this will work because we haven't done a load testing on it, but please let us know if you can access this. Does it show? Okay, so I'll now go into this application. Okay. So as I mentioned, our objective function is really simple, x squared plus y squared. So right now, let's say we set everything to default values. So for Adam optimizer, 0.8, the step size here, and the momentum, something like that, 0.1, and then 0.99. Okay, let's go to this is already 0.1, 8, and 5. Okay. So then you need to select the number of iterations. So it's default set to 5, but 5 is really less. So something has to be like kind of higher than 5. Let's go 17 for now. Okay. And submit. So this application's running. And here. Adam's doing quite well. It's quite a converging faster. This is how I can reduce this size. Okay, so I just stopped. It was just 17. Maybe let's go to 40. Try to do it for 40. Okay. Okay, so this is the situation for SGD and ADMX.
Can you maybe describe for those who don't know what's happening? What is that white dot? What is
So
happening?
the white dot is with each iterations, it's actually getting into new state, and then it's trying to find the minima, right? So the minima is of course, somewhere over here. So we are trying to show that how well these models are performing, or maybe the functions are performing to reach the minima. So sometimes it just went to the minima, then it might have a different, some of these might converge faster to minima and some just might be slower in converging. So this is basically what we are trying to show over here. By adjusting this different values also, you can see if the minima, like if the convergence is faster or it just went into a local minima and it's not moving anywhere. So things like that can happen. So that's basically it. So you can play around with these different height ranges, and then yeah, and we can just check how it's performing or it's just stuck somewhere. So that's mostly it, the app is doing. Okay, so we'll stop sharing now, and maybe we can move into our next. Okay. Okay, so so this is last question. Which Euler scheduler reduces the learning rate when a metric has stopped improving? Yeah, what is the white point? So yeah, it's just it's taking a point in, how do I say? Maybe I have to go to the code. So we define an input, and then it goes into, I can show you where the code is, that's on the code. And it's from there, it's trying to move more into, like with the time, there's a factor of time on that, on the in the equation, and then it's trying to move into, then it's trying to go into a next step, kind of. I don't know if I made it clear. So it's generating an initial point, and then it's trying to like go into new state at every iterations. Okay, so we'll go to the answer. Which one is the answer, Kwame? Was it A?
The right answer is A.
Yeah. Okay.
All right.
Okay. So maybe we can conclude about this topic, and then we can move into the live AI we can show. So Kwame,
right.
do you want to conclude?
Yes,
this?
go ahead. Yeah. Then I will add
Yeah,
some more points. Right?
sure, sure. So optimizers basically are a way where we minimize the loss function so that we can get a better performance on the model. And there are several optimizers such as gradient descent, Adam, Ironstrom, Adamax, and there are many other optimizers as well. So which we use in our hybrid parameter tuning so that we can get the best out of our model. So the uses of all these optimizers based on what we want to achieve. So you have to clear cut definition in your mind that what you want to achieve your problem statement. Apart from that, there are learning rates. So when you don't get a good performance on the model, or maybe you have overshooting the global minima set, then you use this learning rate scheduler so that you can direct your optimizer on where to get the least error and reach the global minima. And it is important to select appropriate optimizer and learning rate scheduler for any task, and wrong choices might lead to slow convergence or even divergence. So you have to understand all the key workings of these optimizers and learning rate schedulers so that you can reach the global minima, which is your objective. So yeah, that's it.
Okay, Terry, do you want me to pull live AI website? Maybe we can share that.
Yeah, we can do that. So basically, so I understand that, and I can imagine for some of you, it's we're just jumping into an optimizer technique. I also realize that it may be something that is new for you. So basically, what you're seeing essentially is I've just given a small sort of analogy that to find your ground truth or to be able to predict as close to the ground truth, like for example, you see pictures of a cat, then you may see a picture of a lynx. It's a funny cat, if you may know, in Canadian and northern Canadian sort of forests, you will see that it has longer ears and whiskers, and there might be other cat-looking sort of animals. And what you want your neural network to do is that if it has various animals from the cat family, and your goal is to actually predict the cat, so the cat families, the felines, the ones that we have in our homes as pets, and lynx are also pets, by the way. I've seen people holding lynx as well, very dear to their in their homes. So in order to make that prediction, you don't want it to predict with a certain confidence a lynx and say it is actually a cat. And that is where you are actually not, so you haven't reached the global optimum with your prediction. The generalization is still not good enough. And that is that whole pursuit of trying to get your prediction closer so that it can predict that it is a cat with close to 99%, 100% accuracy. And that is what actually this whole objective is about, right? So the objective is to you have a network, as in when I say a network, I mean you have an AI model or AI system, let's call it that way. And you need to, have some optimization techniques baked into it. So while you're training your network, your model is constantly learning from its mistake. And the last quiz question was also what that meant was stop a learning rate on plateau. It basically means is that, for example, you have an accuracy, let's say curve like this, on the data that it's a cat. Then you have another accuracy, which is sort of a set, you call it a validation set to teach it that, okay, am I doing right or not? Now, then there is another curve to test against all other cat families. And when you're testing that, then you will see the difference between the accuracy of validation versus the accuracy of the test set, which is the blind set. Now, that difference is where your learning rate, your network has stopped learning. So the learning rate, for example, your learning rate was like this, and then it's like a plateau. It just flattens out. So while it is here, you have to stop it. There are very different techniques in order to, early stopping techniques. You can stop it, and then essentially you go back to your AI model, and then you say, hello, let's try to optimize it. Let's try to maybe decrease the learning rate by another, decimal point, maybe 0.001. And that way you will start seeing that your network in its next iteration will perhaps not plateau as soon as it did last time. And this is how you're trying to converge towards the global optimum, which is the true answer. So essentially, just think of it from that hill analogy that I just gave you, is you want the ball to reach ground zero at the sea level. And as long as it doesn't reach there, there is a lot of room for improvement. Having said that, we do have all sorts of internships. You are free to apply you can send us a mail at contact with your resume, and we are more than happy to look into your resume and give you a fair evaluation of where you stand in your journey with what we're doing. I am going to see if I can, not sure if I can share through this interface. Perhaps, maybe Tanisha, can you share the link of the applied AI?
Sure. Let me pull that.
I do have it here, but I'm not sure why I cannot share through my mobile device.
Yeah, let me share my screen.
That's strange, because I was wondering.
Okay, yeah, here.
Yeah, I mean, if you go, for example, if you click on course and then go to self-paced, and here, if you just scroll down, yes, please, more. Yeah. So, and if you could just those drop-down menus, so program overview. So here you guys can see, and I think this is very important, at any stage, it's important to always go back to fundamentals. So here we talk about, you can play this. Actually, some things I think are already for you to already play and see what are we talking about. And then there's a learning path and all of the course logistics. If you scroll down a little bit more, and then you start seeing these are 4 modules. If you drop down these, so we go into the fundamentals of, what are the sort of, and Python is a very easy to understand language. And then here we give you a bit of an idea. We also give you walkthrough of all the projects. And if you scroll down more, please, then there's a bunch of resources. Then you start saying, okay, so build your machine learning solution. And there, if you can just kind of keep scrolling down, and then so as you can see here, there's the classification problem, all those things. So feel free to send a message to us if you're interested in sort of taking this self-paced program. If you can scroll down a little bit more, and then you see we first touch machine learning, then we touch deep learning, and everything, for example, that you're hearing today about large language models, we've already covered that in module 3, for instance. And then we give you also proper industry-wide projects. So that way, it really makes a lot of it really becomes exciting. So you already see, for example, you have advanced language models, and then going down, there might be, I don't know if you can open that Hive projects, if it does talk about the projects we may have mentioned. And yes, so and since some of the projects are confidential, customers also ask us, well, we want you to solve this problem for us. And this really helps us teach you the real thing, meaning applying AI in industry-wide projects. Many of our alumni from this course have gone and started working in startups in Netherlands and many other countries. If you need, we can get you guys to contact them. These are important things. I say that if you don't have an understanding of AI, you will struggle to become a data scientist. So there is, I would say, a path towards becoming an applied AI expert, because that is what the industry needs. So take a look at it, guys. liveai.eu. That is the website for anyone who's interested. But for this, the 𝗟𝗏scan webinar, I guess the next we will go back into some really interesting things which will be appealing to geologists. So I hope this was a useful session for all of you guys. Do play around with that notebook. Like we said, it's not like we just had a talk and, you guys are left to your own means. That is not the case. There is a GitHub. We've shared the link with you. These are notebooks available online. You can take a look at that. Run them on Google's own collaboratory, and come back to us and ask questions anywhere. Send a mail, or perhaps even if there is a bug or anything, report that on GitHub. So that's going to really help us help you. I thank you all, guys. Thanks.
Thanks.
I believe 𝗁𝗲 had to drop out as well.
Yeah, probably.
So thanks again, and we hope to see you guys again in about 2 weeks' time. We'll be back again. Thanks, everybody.
Thank you.
Thank you. Bye-bye.
Bye.
Bye.